Asking a language model to return JSON does not guarantee that another program can parse the result. In this lesson, we will replace that hope with a decoding rule that blocks invalid tokens while the model generates. I'm Mehrdad. We will trace the process from a schema to a token mask, compare hosted and open source implementations, and separate valid structure from correct content. Suppose a downstream service expects a JSON object with an integer order identifier and a numeric total. A prompt can describe that format clearly, yet the model may omit a required field, return the identifier as text, or add prose outside the object. The response looks reasonable to a person, but a strict parser rejects it. Constrained decoding changes the selection process before the next token is chosen. The model first produces a score for every token in its vocabulary. These raw scores are called logits. The decoder then builds a token mask from the required structure and removes every token that would make the current output invalid. Sampling continues among the legal tokens, so temperature can still change their relative probabilities. Temperature cannot bring a block token back into the candidate set. The model still chooses the content, while the mask enforces the allowed structure. If this explanation is useful, like the video and subscribe to follow the series. There are 3 common levels of control, and each one solves a different problem. Prompting describes the requested format in natural language, but the model can still ignore part of that instruction. JSON mode adds a syntax requirement, so the response should be parsable JSON rather than ordinary prose. It does not necessarily enforce your required field names, data types, or allowed values. Schema-constrained decoding adds those supported schema rules during token selection, which prevents many malformed objects before they are produced. Application validation still remains necessary after generation. It checks business rules that the schema cannot prove, such as whether an identifier exists or whether a total matches the source records. When schema constraints are available, use them for machine-readable structure and reserve repair logic for unsupported features or exceptional responses. This separates 4 jobs clearly. The prompt explains intent, the decoder enforces structure, the validator checks meaning, and repair handles the remaining failures. Now, let's follow the schema from the request to the next generated token. The schema defines the object structure, including required keys, value types, and any supported limits on those values. The decoding system converts those rules into an internal grammar that can answer one question repeatedly: which tokens may legally come next? The answer depends on the text generated so far. After an opening brace, for example, the grammar may allow a required property name, but block an unrelated word or a closing brace. The engine compares that legal set with the model's vocabulary and creates a mask for the current decoding step. It applies the mask to the logits, removes invalid candidates, and samples from the candidates that remain. The process repeats after every selected token until the object is complete. This mechanism enforces syntax and supported schema rules, but it does not decide which valid value is factually correct. Your prompt and input context still guide the model toward useful values. Modern engines reduce the added latency by caching repeated grammar states and preparing masks alongside model computation. You provide the schema, while the serving system performs these checks during generation. Hosted model providers usually expose constrained decoding through a schema option, instead of asking you to manage the grammar engine. With structured outputs, you send a supported JSON schema together with the request. The provider constrains generation, so the returned object follows that schema. Strict tool arguments apply the same idea to function calls, where a tool expects specific parameter names and data types. This is stronger than JSON mode, because parsable JSON can still contain a missing field or the wrong type. The stronger guarantee also has boundaries. Providers support only a defined subset of JSON schema, so an unsupported keyword or deeply nested design may fail when the request is prepared. Safety refusals and other exceptional responses may also use a different response format that your integration must handle explicitly. Treat schema acceptance as part of deployment testing, rather than assuming every schema transfers unchanged. For normal responses, constrained output prevents many parser failures at generation time. your application should still detect refusals, validate business rules, and record any response that does not match the requested schema. Open-source serving systems expose the same basic mechanism, but you can often choose or configure the grammar engine yourself. XGrammar is one widely used engine for converting a schema or grammar into token masks during decoding. Serving projects such as vLLM and SGLang can use this kind of backend to produce schema-constrained output from locally hosted models. The model still computes logits in the usual way. XGrammar tracks the current grammar state, identifies the tokens that remain legal, and supplies the mask before the serving engine selects the next token. Its performance work focuses on reusing earlier mask calculations and running grammar-related work alongside model computation. The practical lesson is not that every open engine behaves identically. Supported schema features, configuration options, and integration details can differ by version. Test the exact model server and schema combination you plan to deploy. A hosted provider manages this decoding layer for you, while an open stack gives you more visibility and control over the same core process. Once parser errors disappear, the remaining failures can become harder to notice. A response may contain every required field with the correct data type and still be wrong. The model can produce a valid customer identifier that does not exist, a numeric total that does not match the invoice, or an allowed status that contradicts the source record. Constrained decoding cannot reject those values when they are legal under the schema. It only knows the structural rules available during token generation. This creates two separate checks in a production system. Structural validation asks whether the object follows the schema. Semantic validation asks whether each value is supported by source data and satisfies the application's business rules. Keep both checks visible in monitoring because a successful parser result says nothing about factual accuracy. Schema design also has practical limits. Very large schemas, deep recursion, and unsupported combinations of rules may exceed what a provider or grammar engine accepts. Use the smallest schema that expresses the interface your software truly needs. Then verify identifiers, quantities, permissions, and policy decisions against authoritative data outside the language model. Some applications need natural language text and machine-readable data in the same response. An agent might explain what it found, then return a structured tool call that another service must execute. Applying one grammar to the entire response would prevent the model from writing the explanation freely. XGrammar 2 introduces structural tag for this mixed format. The decoder leaves ordinary text unconstrained until a designated tag begins a structured section. At that point, it switches to the grammar assigned to that tag and constrains the fields inside the section. When the structured section ends, generation can return to ordinary text or move to another defined format. This approach is useful when an agent can choose among many tools, because each tool may require a different argument schema. The implementation can share repeated grammar components, instead of compiling every tool definition independently. The design rule is straightforward. Allow normal language, where people will read the response, and enforce a schema where software will consume it. The boundary between those regions must be explicit and tested. Remember 3 ideas from this lesson. First, prompting describes a format, while constrained decoding blocks tokens that would violate the supported schema. Second, the serving system turns schema rules into a new token mask at each decoding step, then selects among the legal candidates. Third, valid structure does not guarantee correct content, so your application must verify important values against trusted data. In the next lesson, we will move from output control to serving throughput and examine how a scheduler manages key-value cache memory under concurrent requests. I'm Mehrdad, and I'll see you in video 12.